Okay.
And it says you're live or on
All
the air.
right. Very good. So I want to thank everybody to come and celebrate with our good friend Barry on the release of his new book. I'm going to just give a little introduction to him, and he's got a few words to say, and then we can talk about the book, or we can talk about quantum, or whatever. So, Barry Burd received a master's degree in computer science at Rutgers University and a PhD in mathematics at the University of Illinois. You're a Chicago kid almost.
Well, I wasn't native at the time. I came from Philadelphia, but
That
I do really like Chicago style pizza.
is as a teaching assistant in Champaign-Urbana, Illinois, he was elected 5 times to the university-wide list of teachers ranked as excellent by their students. That's pretty impressive. Since 1980, Dr. Burd has been a professor in the Department of Mathematics and Computer Science at Drew University in Madison, New Jersey. He has spoken at conferences in the United States, Europe, Australia, and Asia. In 2020, he was honored to be named a Java champion. Did you get like a a button or a badge for that? That sounds cool.
I got a shirt and a jacket.
Beautiful. Dr.
Not
Bird,
it's not nearly as good as being a member of the Académie Française and being able to wear
uh,
a costume and a sword.
Dr. Bird lives in Madison, New Jersey, USA, where he spends most of his waking hours in front of a computer screen. Welcome to our world, said the mouse. Um, so, Barry, I noticed this is the first time I reviewed this from your book, and so they in this particular book sometimes they have a little acknowledgement section, and I didn't realize they just tacked it on to the bottom of the about author, and there are some names in your acknowledgement, people that are in this room. Write this and
All
such
right,
like,
here, yes.
and I'm so happy that I just noticed that. So.
There you go.
Uh, and so now I will turn it over to you.
Okay, I'm going to share my screen, of course. What else does one do at a meeting like this? And there is my beautiful opening slide. Let me do something here to make sure that, there we go. All right. Well, listen, I have to start with a confession. The confession is that when I was asked to do this um, book launch event, I said, no way, I'm not a marketer. So I stick by my story there. I'm not a marketer, but I'll be happy to tell you a little bit about the book, and you can save your applause till the end or whatever you want to do. It says at the bottom, I am Barry Burd. I've taught for longer than anyone can remember at Drew University. And if you want to reach me, then all you have to do is remember my name, barry@burd.org, and make sure it's BURD. That's very important. Um, I have this book now called Quantum Computing Algorithms. I even have a real copy of it, which took a long time to get, actually. Ron, I think you got your copy before I did, right?
I believe that is the case.
Okay.
I have some people pinging me asking for that password. So if you could drop it in the chat if you have it.
Well, the password to do what?
I guess they're clicking on the link and it's asking them for a password.
Okay,
I
let me
don't.
see if I can.
It didn't do that for me, but
Let me see what I can find here. If you click on the link, give me a sec. Needing information.
Did you require, Barry, did you require that everyone be logged into Zoom to connect? And if so, maybe
everyone has to be, it's Zoom. I did not advertise the YouTube link. I didn't even set it up until a few minutes ago, but in the chat.
So what I'm getting at is that it could be Zoom asking for the Zoom password.
There's just one person on on, give me a sec here. Chat. Okay, show the
Yeah,
chat.
I didn't,
I'll type the password.
I didn't get asked the password, but maybe it auto.
There
log
it
in.
is. There's the password.
Okay. All right. I will copy that to where it needs to go. Thank you.
All right. And why they would need that with the link that I supplied, I'm not sure. But okay. And I want to remind everybody that I really like being interrupted. It lets me know that you're awake and that you're understanding what I'm doing. Feel free to interrupt me if you have questions, if you don't understand something that I'm saying, or you want to add something, or you want to ask, well, whatever. I just, let's make it a conversation if we can. So anyway, the first question that I want to answer is, why did I bother to write a book? Well, I should go into a million details here. What I should say that I became interested in quantum computing because I was sitting in a doctor's office and saw a copy of Nature magazine and read an article and said, wow, that's really interesting stuff. Fast forward to a couple of years later, and I was trying to teach a quantum computing course for undergraduates at Drew University. But Drew University is a small college, and it's a liberal arts college, so it's not a technical college, which means that in order to have an elective course meet, you have to make it so that a wide variety of students can take it. If I made it very specialized and required abstract mathematics, it would be unlikely that I would be able to attract enough students to offer the course. So I needed to figure out a way of presenting quantum computing that didn't involve having to take linear algebra first. And also, the other thing that I really, really wanted to do, a lot of these students had taken classical computing, knew how to program in Python and Java and maybe other languages. And I wanted to give them a feeling for why quantum algorithms work. What's the secret sauce? What's actually going on behind the scenes? I can read the mathematical formulas that lead me to conclude that Deutsch's algorithm works, or that lead me to conclude that Grover's algorithm works. But until you've studied them for a while, it's hard to really get the intuitions. What's going on? Is this just a coincidence that this is working? What's happening? What's going on behind the scenes? Quantum algorithms are really difficult to develop. A lot of the thinking that you do to develop a quantum algorithm isn't quite scalable the way the thinking that you develop a classical algorithm is. So I wanted to, number one, offer a course that was somewhat precise in its explanation, not just fluff, but didn't involve linear algebra, didn't involve any abstract mathematics, but also that gave students some intuition about what was going on and why these algorithms worked. So what did I do? I started working on the course. A couple semesters later, the people from Pact Publishing sent me an email, said, would you like to write a book about enterprise Java? I said, no, but I do have some ideas about a book for quantum computing. Here's my ideas. They said, we love it. Why don't you write a book? I started writing the book. I got done with the book back in August, and now it's in publication. I have lots of stories about writing books. I've written Java books. I've written in the For Dummies series. This was a different experience. They're all different experiences. But anyway, the whole idea of the book is to sort of have an intermediate level quantum computing exposition, not just the fluff that you read in some of the magazines. Fluff, I shouldn't say that. Not just the popular overview that you read in some of the magazines, and not expecting people to understand any abstract mathematics, and yet still using mathematics to make the arguments precise. So let's take, for example, the way I describe Deutsch's algorithm in the book. Take a look at these two diagrams. They were mostly generated by IBM's Qiskit platform. The only way that I tweaked these diagrams, and you can see my little pointer, right?
Yep.
Okay. The only way that I tweaked these diagrams was that I found that.
So sorry.
Hello?
So if you guys aren't making a specific comment, please mute your microphone so we don't hear your background noise. Thank you.
Okay. The only way that I tweaked these diagrams is that if they just pop up in a book, and there they are, you don't even get to see them. You don't even get to see them rendered on a screen as a result of a run. It's often hard to tell whether an arrow like this is pointing toward the back of the sphere or pointing toward some other place on the sphere. So in order to emphasize that it was pointing toward the back of the sphere, the negative z axis, I added these little dashes. I kind of made it a dashed line indicating backwards. And I did the same thing here and here. And there's an explanation in the book that says, well, these are almost the diagrams that you would see with Qiskit. But anyway, in order to explain phase kickback, to first give the idea of what happens, I've got two circuits. One of them doesn't have a C0 gate. The other does have a C0 gate. And look, over here, you see that qubit 0, which is Q0 for me, is facing front. And in the next diagram, after you add a C0 gate, you see that Q0 is facing the back of the sphere. And that's counterintuitive if you are used to the standard description of the C0 gate, because the standard description of the C0 gate says that what's going to change as a result of executing a C0, applying a C0 gate, is that the value of Q1 might change. But here in this case with phase kickback, what happens is that the phase of Q0, the phase of the upper qubit changes. So that's how I introduced the idea of phase kickback. Now then, on the next slide, we've got some math just showing that it works. And again, matrix multiplication, tensor product, and ordinary matrix product. So we start off with a minus and a plus, and we end up with a minus and a minus, which corresponds to the diagrams that came on the previous slide. So you see here, if I have introduced the matrix operations, then that previous slide's illustrations make sense. And then in the book, I have to say, well, isn't that counter to what you know? But look here, now you believe it. I'm not making this stuff up. And so then we can march on. Now, once we've got phase kickback under our belts, we can go on and talk about Deutsch's algorithm. And again, what I want to do, and I do use, some math here, some equations. Again, nothing abstract, just matrices and cats. What I'm trying to do is give an intuitive idea about why Deutsch's algorithm works. And I've seen so many online explanations. This was mine. With Deutsch's algorithm, you have, at least in the, with Deutsch's algorithm, you have 4 different possible oracles. 2 of them constant, and 2 of them balanced. And what we observe from looking at these diagrams, after going through them and understanding why these diagrams are the ones that form the oracles that we're looking for, is that you can recognize an oracle that's working on a balanced function if you can see inside it and notice that there's a C not gate. Well, how do you find out if there's a C not gate? You look and see if this cubit is pointing to the back of the sphere. You look and see if this is the minus sign ket instead of the plus sign ket. And you can find that out by applying an H gate right here. So when the reader is done with that chapter, what I feel and hope, passionately hope, is that by comparing the constant oracles with the balanced oracles, it makes some good sense why it is that Deutsch's algorithm works. It's not just a weird coincidence. It's not just magic. It's not just a bunch of equations. It's this kind of sensible way of checking to see if you have a C not gate in your circuitry or not. A C not or not. Okay, there's got to be a pun there, but I'm not thinking of it. Am I making sense?
Maybe this might be like for some elementary, but what is the idea of the C not gate versus the just a balanced or a regular gate? Is it as far as truth tables go?
So the purpose of the C not gate is that you're sending a qubit along this line, right? And another qubit along this line. And to those of you who don't like the idea of sending them along lines or having this be a gate, I apologize for my abuse of terminology. Let's say that there's a 0 coming along this line.
Okay.
Then the C not gate does nothing.
Okay.
Let's say that there's a 1 coming along this line. Then the C not gate flips whatever is along this line. So it's called a C not gate because it's a controlled not. You flip, you apply a not operation to this line just in case there's a 1 coming along this line. It's a conditional flip.
Okay, so in a sense, if this was kind of like a classical computing where X and Y were like signals, the Y you don't really normally the Y you don't really care, but it does affect what you're going to get out from X. So if the X is 1, and the Y, so it's like X equals sorry, not X, or Y. Sorry, or not Y, or something towards that. Basically, like it's only like the only time that you'll get the X value is that if you don't have a Y value, but you do have a X value. Correct? Or am I incorrect on?
I have to confess that I'm having trouble following.
Can I step in for just a quick one?
I just want to, before you step in, let me just add that I went through that explanation. Sort of when I did, I sort of assumed in advance that I made the assumption that people already were exposed to Deutsch's algorithm. If that's not the case, I apologize. But anyway, Ron, go ahead.
So when you start learning about quantum, there's a real heavy tendency, especially if you come from a classical hardware background, to want to map classical hardware into quantum circuits. And I'm going to tell you right now, stop. The only thing that you can, in my opinion, that you can borrow from classical digital hardware is the Boolean math. You know, the logic translates nicely over to quantum, but the thing that you're looking at, you're probably looking at these diagrams and you're calling them circuits. They're not really circuits. So
Called circuits, but
yeah, I'm gonna leave it at that, and we can discuss that more of that after when we get to the Q&A or the open discussion.
I'm home, but I'm just,
hello, you just muted yourself. Michelle?
yeah, sorry about that. Yeah, I was just trying to understand. So basically, like, it was about Boolean algorithm. I just had kind of a phone call. That's why I did my.
Oh, okay. Yeah, to answer your question, there's a lot of hocus pocus going on here. Things that involve what I expose in the book as matrix arithmetic.
Okay.
Essentially, what happens is this whole combination of x and y is represented as a vector or a matrix. The action inside the box is itself a matrix, and when you apply this C0 matrix to this configuration, which is the starting configuration of the two qubits, you end up with this thing. And what this thing does is it pulls some kind of a change on the thing that we call the control qubit. So it's as if I'm trying to control a cat. Here's me. Here's the cat. I'm trying to control it. What ends up happening is I'm the one who gets scratched. And the cat stays the same. And that's the phenomenon that's happening here with this circuitry. Does that analogy make sense?
Yeah, I think so.
Okay. The upshot of it is that in Deutsch's algorithm, what you're trying to do is, in one step, decide whether the circuitry inside this box, and again, sorry, Ron, for using the word circuitry, whether or not the circuitry inside this box implements a kind of function called a constant kind of function, or a kind of function called a balanced kind of function. And what I'm doing in this chapter is saying, look, with Deutsch's algorithm, really what we're doing is observing whether or not we have phase kickback. And if we have phase kickback, then there's a C0 gate in there doing the phase kickback. There's me and there's the cat. And then we know that if there's a C0 gate in there, there's a balanced function.
Okay.
Okay? Yeah, this isn't going to be Schrodinger's cat. This is going to be Barry's cat. I just coined a new technology. Any other comments? I have other examples of this, a few others. Okay, here's one of my favorites. The first algorithm that I ever understood really was Grover's algorithm. What the heck's going on there? Again, I'm going to aim my discussion in this group mostly toward people who already know what Grover's algorithm does. I'm not explaining Grover's algorithm from scratch, just as I didn't explain Deutsch's algorithm. But if you want to know more, then feel free to ask questions if you have them, or send me email, or whatever you want.
Or buy the book.
Or right, there you go. Right. That's it. I'm leaving out information so that you have to buy the book to understand it. Look, the numbers along this line represent probabilities. This slide is actually fancier than what I can do in the book, but I try to emulate the slide like this with illustrations in the book. So you have 8 things, and one of them is special. One of them is the one that you're searching for. These are 8 customers, and you want to find the customer named Joe Dodge, because you want to make a phone call to Joe Dodge and have him get out of Dodge. But anyway, what you do is you have, again, what I'm going to call some circuitry that sets Joe Dodge apart. Now, what sets Joe Dodge apart is that, once again, his little sphere goes from the plus side of this, his little arrow goes from the plus side of this sphere to the minus side. And to go to from the plus side to the minus side, we're going to represent that by saying that Joe's line moves across here and becomes this thing, which I've marked in red. So actually, I take back what I said. There aren't 8 sticks here. There are 7. And we had a piece of circuitry that moved one of them, turned one of them around on the sphere, and brought it over here. Now then, what I have to do is convince the reader with examples, matrix examples, to show that we can do the following operation. We want to find this red one. We want to find this one that's different from all the others, Joe Dodge. And now normally, if we were doing a regular search through a linear list, we might not find Joe Dodge until he might be the 8th person, right? So we might roll 1, 2, 3, 4, 5, 6, 7, 8. 8, that's Joe Dodge. But I want to find him in 2 steps. And what I want to do in this slide, and what I try to do in a sequence of diagrams in the book, is intuitions about how a certain operation that I can do with matrices helps me find Joe quickly. So this number 0.35 sort of represents the probability of my seeing any one of these when I measure the system. I could see any one of these when I measure the system. This number, 1 over square root of 8, 0.35, that's the square root of the probability of seeing any one of these. Over here, this minus 1 over square root of 8, just because he's on the opposite side of the sphere doesn't mean that he doesn't have the proper probability of 1/8 of being seen. So right now, if I measure this system, what I'm going to see is one of these sticks. And I have a 1/8 chance of seeing any of these and a 1/8 chance of seeing Joe. And I don't want that. I want to have a pretty good chance of seeing Joe. So what I do is I do a matrix operation that finds the, I'm going to switch here, pointer options. Undo laser. Yeah, I'm going to do a matrix operation that finds the average of all these 1 over square root of 8s and this minus 1 over square root of 8. It's going to be pretty close to these fellows. And the matrix operation is going to twist this whole system around like that. It's called inversion about the mean. And now look what I've got. I've got all the non-Joe Dodges at very low probability, and I've got the Joe Dodge at a much higher probability. The probability when I measure the system of seeing Joe is close to 1, but not exactly 1. So what can I do? If it did something good for me one time, I'm going to do it again. Let's see. I'm going to apply an operation that moves Joe to the other side. Again. Now I have all these fellows over here, and there's Joe. And then I'm going to find the average again. And then I'm going to rotate around that average again, inversion about the mean. And what I do in the book is show I can do this with matrix multiplication. Boom, very close to 1. So the idea now is that when I measure this system, I have a close to 1 probability of having Joe Dodge be the answer, and a close to 0 probability of having anybody that I'm not looking for to be the answer. And that's the intuitions behind Grover's algorithm. Now, what I do in the book is explain all this and try to build people's intuition. Again, it's all with matrix multiplication.
Excuse-
So
Yes.
two things, Barry.
Yeah.
First of all, I hope you'll share your secrets on how you made this animation.
Okay,
Yeah.
PowerPoint actually has a lot of good.
Wow.
Yeah.
Okay. And second, one thing that this shows about Grover's algorithm is you'll see in a lot of the text where they talk about how many times do you run Grover's, and you compute K, right?
Yeah.
And this visualization is beautiful because you can see that when all the non-Joes go negative, you're done. Because if you continue the algorithm, it'll start heading back in the wrong direction.
Right.
And that's where it shows you why you got to calculate K for the number of iterations. It's just it's just right there. The visualization shows you why it has to stop there.
So with this visualization, what I'm able to do is argue pretty convincingly that the number of times you have to do this inversion about the mean is proportional to the square root of the number of things that we're starting with. So if I have 8 things, then square root of 8 and do a little floor and ceiling stuff, and you have 1 or 2. And if you have 100 things that you're looking through, then you're going to do, I don't know, I can argue that you'd only have to do the inversion about the mean about 10 times. So with this illustration, I can talk about square root. The real Grover's algorithm formula is pi over 4 square root. And for that, I have an extra little section where I argue somewhat in a glossing fashion. Yeah, I argue roughly with a geometric argument having to do with angles that the pi over 4 enters the picture. I admit it. If you don't use abstract mathematics, you are limited. It's not going to take you all the way to the finish line if there is one in quantum computing. But being able to show square root with something like this is I think, pretty good. Questions or comments?
Maybe a question and a comment.
Sure.
If you can kind of show like what happens if you do one more iteration beyond this, just to kind of give us the idea that if we wanted to get closer to 1, you won't be able to.
So I don't have more animation to do this, but let's try to figure out what's going to happen. Right now, we've got all the non-Joe Dodges over here, and we've got Joe over here, right?
Right.
Now, what's going to happen? When I tend this to the negative side, right? Remember that what I did was I took Joe and I moved him to the other side here. So I'm going to do that again. Let's visualize this. This red one, right, comes over here, right?
Right.
And now the mean then, the average, right, is going to be right there.
Okay.
So when I rotate around the mean, can we visualize what's going to happen? Joe is going to end up, so the little triangle, right?
Yes.
Is here. Joe is going to end up passing the triangle, right?
Okay.
And going the same length over here on this side. And I think he's sort of going to end up here, roughly. Right?
Okay. So then we will.
He's going to go around and kind of end up here, like that. which means that we've done worse for having done 3 iterations instead of 2.
Okay. Now,
Yeah. So once again, this visualization of how that works, it immediately slaps you in the face because the first step is to rotate about 0, and the second step is to rotate about the mean. So as soon as if you had done one more animation, you'd see that we've ruined the prediction. We were really close to one, and now we've drawn it back. And the thing is, if you keep doing it, it'll go completely in the wrong direction until it flips back again, and then given a certain number of more cycles, you'll come back to the perfect thing. But you don't that's pointless to do, because the whole thing with quantum is you want to get this done in the demonstrated square root over whatever steps instead of the classical number of steps.
okay. And then another question is, what if you had, instead of just 1 out of 8, you maybe had like a 3 out of 8 that you wanted to actually look at? Would the Grover's algorithm still be as valid, or if you kind of did the same rotation about the mean?
I'm going to confess that I don't remember if there's an enhancement to Grover's algorithm that's meant for more than one.
There is. It requires more circuitry. It requires some ancilla bits, but it works exactly the same way. And then instead of moving 1 Joe around, you're moving 2 Joes around. But
Joe's definitely going to get tired.
most of the texts don't never they'll talk about that, but they won't actually show it. There are things out there like I'm actually looking at a string comparison, a bit string comparison algorithm, which uses Grover, and it actually works just exactly the same. So
now, one important factor about quantum computing here is that if you're doing a classical calculation, you expect to get an exact correct answer, or at least if you run the same program and you run it twice, 3 times, 4 times, and if there isn't any sort of random input to the program, then you're going to get the same answer each time. Not true in the quantum world. For example, this Joe here is close to 1, but not exactly 1. So I don't remember the how close to 1 Joe is, but there's still a small probability that when you read this system, a very tiny probability, that when you read this system, you won't see Joe, you'll see one of these fellows. And to handle that problem, what we do in quantum computing is we run an algorithm like this several times. We call it several shots. Sorry about the terminology. We run the algorithm for several shots, and we try to see what answer we're getting most of the time. That's the way quantum computing works.
How do you determine how many shots to run?
That's for the statisticians to determine. I'm not a statistician, although sometimes I've pretended to be one. I just run my examples 1,000 times, and usually the answer is just so obvious. But I'm sure that that's not the right way to approach it.
I think it's basically, because it's a stats, you probably want at least 2 to 3 standard deviations.
It depends. It depends always on the extent to which it matters whether your answer is correct or not.
Right.
If you're controlling a heart-lung machine, you want a lot of standard deviations beyond the mean. If you're just trying to decide what to have for dinner, a couple of shots will do it. A couple of shots to decide, and then a couple of shots after dinner.
So when running a simulation, you can actually experiment with this and see where things to go, whether they converge or diverge, right?
Right.
Can't you also run the algorithm in parallel, especially, I mean, if you have like the, if you have the circuitry where you can kind of have each of the different items duplicated in each of the circuitries, um, you could run this in parallel because none of the other the qubits would actually kind of affect each other um, in like an enclosed algorithm, and then yeah, basically like you can get the average of which ones uh, what was the right probability or what was the thing that actually got correct.
Well, one of the foundational ideas in quantum computing is that qubits can be entangled, which means that essentially what it means is that one operation can affect many, many qubits at once.
Okay.
So this action here, where we're doing the rotations, and for your visual pleasure, I can do it again. I like to do it. It's not exactly Disney animation, but hey, what the heck?
It's PowerPoint animation.
Yeah, it's kind of nice. I was kind of surprised to. Yeah, there we go. Yeah, so cute. But that whole spinning of all those qubits is happening in one matrix operation.
Okay.
So talk about parallelism. All that's happening at once. We're not manipulating each qubit separately.
Right. But I was saying like you could have a bunch
Several of these.
I was saying you could have several of the same circuit or several of the circuits happening simultaneously, both initially with the same data or the same system inside of the qubit, and then you're doing that same operation, but each of these systems are independent of each other. That might be a way you can kind of have the little bit more guarantee of or have a little bit of like the ability to compute, what is the correct answer, what is the correct.
Yeah. So once again, you're thinking classical. So save that thought for the end, and we can talk about it.
Okay.
Okay.
Now I have a few things to say about that. We'll talk about it, but please remind me about that point because you have sparked two thoughts in my brain, one that's saying yes in one way and the other that's saying no in another way. And I want to articulate them both after I'm done with one more example. Okay?
Okay.
All right, here we go. Let me get back to this thing, and we're going to march on to another slide. Now, Shor's algorithm is the killer app for, again, the terminology. Sorry about the militaristic terminology. Shor's algorithm is the app that made quantum computing famous. And man, it's difficult to explain that in a way that rings intuitive ideas into people's minds. But one aspect of Shor's algorithm is the notion that so Shor's algorithm is the algorithm that you can decrypt things like RSA encryption in seconds once we have enough qubits. And we cannot do that now. Now, if we tried to decrypt RSA, it would take billions of years, millennia, whatever's eons. With Shor's algorithm, we could do it in seconds, but we don't have enough qubits yet to be able to do that. But anyway, one important aspect of Shor's algorithm is period finding. And period finding is the flip side of frequency finding. So what I'm going to try to do here in this slide is illustrate how I can decide that there are 4 repetitions of something in this vector. So I've got 4 repetitions of 1, 5, 1, 5, 1, 5. And I want to do it in what is essentially a matrix multiplication. Now, what this involves is big matrix with complex numbers that, well, first of all, complex numbers, get scary to readers. We shouldn't have called them complex. We shouldn't have called them imaginary. That was a bad idea to begin with. But anyway, that makes them scary. And there's a lot going on here. So what I want to do is get it so that I can make sort of clear what's happening when you create a matrix like this called a quantum Fourier transform or an inverse quantum Fourier transform, and you multiply it by a vector like this. So, and this only works for 8 values, 4 values or 8 values. It's going to be too crazy if I have 16 of them, but that's okay. What I did was created this font. Actually, this is a font. That's how 0 is represented in the font. That's how 1 is represented in the font. So these are actually characters. And if you look at these without having the specialized font, you'd see 0, 1, 2, 3, 4 here. But actually, what these represent are complex numbers that are kind of going around in a circle. And the speed with which they go around in a circle are, well, here they're pretty slow. And here they're faster going around counterclockwise. And here they're even faster. They're going around, they're flipping from 3 o'clock to, I guess, 11 o'clock there or something like that. And then quickly down to 6 o'clock. So they're going faster here and even faster here. They're going from 3 o'clock all the way around to 9 o'clock and then 3 o'clock again and 9 o'clock. And everything that's black, everything that's a black square is something that I'm not concerned about. If there are circles going on there and same pattern, yada, 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 but I don't want to get distracted by it. So what I'm going to do now is multiply these things by these things. And my matrix ends up having these 4 rows among other rows. And how in the world am I going to explain Shor's algorithm by doing this? Well, if you look at these things, let's take a look at this 1 row, then you can discover that there's a lot of cancellation going on there. For example, between these 2 pieces, this one and this one, I'm multiplying 1 times 1 o'clock, 3 o'clock. And over here, I'm multiplying 1 times 9 o'clock. And it turns out that if you look at these as complex numbers, one of them ends up being positive and the other ends up being negative. So these 2 things cancel out. Now, again, I'm not going into details here. What I'm just saying is that we can visualize the cancellation by comparing this 1 pointing east, the 1 multiplied by pointing east to this 1 multiplied by pointing west. And if you notice, we've got cancellation going on everywhere. For example, here's 5 multiplied by pointing in, I don't know, toward 130. And here it gets canceled with 5 pointing toward 730. But this circle and this circle point in opposite directions. So it turns out, and I argue this mathematically, that these 2 factors, these 2 terms cancel out, just as these 2 cancel out and these 2 cancel out. And if you look at what happens in this row and the next row and the next row and the next row, that's what you see. You see cancellation in the rows that I've numbered 1, 2, and 3, but you don't see cancellation in the row that I've numbered 4. And that's where you sort of get this resonant frequency. At that point, instead of all the terms canceling one another out, they all end up sort of helping one another. You don't see the same cancellation. This one and eastward pointing does not cancel with this one and eastward pointing, or with this one and eastward pointing, or with this one and eastward pointing. So it's the 4, it's the row number 4 here that ends up being the first non-zero value in the vector. Don't look at this one. This one doesn't count. This 4 ends up being the earliest non-zero value. All the others, it's going to be a 0 here, a 0 there, a 0 there. So here's what we've got. We've got something that I'm going to ignore here, and a 0, and a 0, and a 0. And then here we get a non-zero number, and we look and say, oh, that's the 4th entry in the vector. Well, 1, 5 occurs 4 times. Whoa, we found the frequency of the sequence in the vector. Pages and pages later, we show how finding the frequency of the sequence in a vector gives you a good shot at being able to factor an extremely large number into 2 primes, which is the way that you can decrypt an encrypted message using RSA.
Could you actually, when you're doing the decryption, if you use a small enough key just to kind of verify to make it a lot more simple to kind of prove Shor's algorithm works, would that be a way you can kind of do that versus kind of brute forcing it with the RSA algorithm? Because I think
absolutely. Now I have examples in the book of 15 and 25, and I have examples of some larger numbers to try.
Okay.
It's not difficult to do if the numbers that you're working with are rather small. But this algorithm is particularly challenging to describe because the numbers that you're working with really, really quickly become very large and unmanageable intuition-wise and even paper-wise, even visually. But the real power of this algorithm is when you're talking about numbers that are 2048 bits long, and you have to start factoring them.
Excuse me, but could you also kind of use this to verify or like look at maybe larger numbers that might not be like really like you're basically I'm trying to figure out like a numbering system where I've only found like 3 numbers that actually kind of meet the requirements where basically the all the numbers that are prime are actually factors of either the base or 1 minus the base. The ones that I found were 3, 6, and 4, but I'm just trying to figure out if a number like if there would be a much bigger number that actually has some value that all of the primes that are less than the number are factors of either itself or 1 minus or the number before it.
I think you're going to have to ask that question again.
So basically, I'm just trying to figure out. I wanted to kind of do this as kind of an experiment or like a. Basically, I want to figure out like a numbering system or a base numbering system where all numbers that are all of the primes that are less than n or less than the base are either factors of the base or factors of 1 minus the base. So
all primes that are less than the base.
Right. For example, 6. 6,
I see what you're talking about, yeah.
So basically, I kind of I've so far tried to use like more or less like a brute force approach, but I know like if you do that for like a really big number, um, you won't be able to do that. But I'm just trying to figure out if there is another number that's way bigger, or if those are the only three numbers uh, that are kind of going to work: 3, 4, and 6.
I need a number theorist. Is there a number theorist in the house?
There are plenty on YouTube. I think this has been discussed over there in a couple of different formats. But I mean, is it your point to find large prime numbers?
Well, I'm actually I probably, yeah, I do want to find large prime numbers, or actually not large prime numbers, but I want to find numbers whose large numbers whose factors of it, all the prime numbers that are lower than it are either factors of itself or the one minus itself.
So this must be a famous problem. Am I right? Is there a name for such a prime?
I don't know.
Oh, okay.
This is something that I found out myself. I just kind of, and if you do find that, you can kind of, factor out all numbers that are less than the square of the base, as either prime or non-prime. Um, and if that would kind of give you a greater coverage. Once you go beyond that base, it's kind of a little bit up to it's a very difficult to do. For example, if you use a base 6, you could find up to 36 whether a number is prime or not, just by looking at what are the components of it, whether the sum equals to 5 when you do that computation, or whether the last digit is equal to 2 or 3. Yeah, 2 or 3. Or kind of a multiple of 2 or 3.
Okay.
So it's kind of just more towards number theory, but it does mean that I do want to compute find like a number or something, search a number where its factors are its prime factors are its all prime factors are covered by all of the primes that are less than it. And I know, going through huge numbers, it's kind of not worth it. If
Well,
you're
so in theory, you can use Shor's algorithm to factor large numbers, but it's probably going to be a lot of extra work to find all the primes below a large number, because
Okay,
Shor's will give you one set of factors at a time, I believe.
okay. But, yeah, thanks. I just was
If
kind
you
of
run Shor's algorithm more than once, each time you might not get the same answers each time. For example, I ran Shor's algorithm with 15. Sometimes I got 5, sometimes I got 3, sometimes I got both 5 and 3. Just sort of, again, it's probabilistic output.
okay. And kind of like when we're looking at this, um, the kind of the complex numbers, could we kind of imagine that these complex numbers are like a single unit or units along the uh, units along the values along the unit circle?
This is
So
the unit circle.
right.
This is a picture of the unit circle.
So
And
the
pointing east is 1, and pointing north is I, and pointing west is -1, and pointing south is -I.
okay. So this basically like the value would be just any place on the unit circle.
Yeah, right, exactly. I've taken the roots of Unity and made a font, a TTF font out of them, True Type font.
Okay. Would yeah, so would the would this also be valid if you were using quaternions, or would this kind of degrade across if you're having some sort of quaternions?
Can't say. I mean, I said that this is good for 8 and it's not good for, say, 16. I'm not talking about quaternions now. I said,
No,
yeah, I said that this is good for 8 and not for 16. It's just because by the time you have 16 of these, it becomes difficult to see where the thing is pointing and what cancels with what else. That's independent of your quaternions question.
no, I was just I was asking because like with the short, if you kind of basically you're talking about complex numbers, and it seems like a lot of these values are kind of dealing with like a unit or kind of like a circular motion. If you had a quantum or a quaternion, usually it kind of implies a rotation across an arbitrary axis. So you can kind of maybe see like it in a uh, three-dimensional uh, unit, and maybe like you have like a video graphic, dealing with the with these algorithms in kind of like a application, probably connected to a a maybe like a Vulkan or some sort of rendering issue where you can kind of show how these work in like a simulation, how it would go in and do the computation through the simulation.
Yeah, I don't know if that's going to help you here because the quantum Fourier transform that's used in Shor's algorithm is specifically um, um, roots of unity and complex numbers. So
Okay.
it's specifically the unit circle here.
Right. So most of the quantum computing, we should kind of think of everything in more of a circle, not a sphere.
Oh, see, the sphere comes in here. There are the spheres. Now,
Okay.
for your information, I had some students who are wizards at using Unity software make me some spheres, some animated spheres, and there's a piece of a library in Unity that actually turns a diagram into an anaglyph. An anaglyph is red blue glasses so that you can see them in 3D.
Okay.
So I had my students in one of my quantum computing classes looking at these spheres in 3D. And I must say, I don't think they learned much more about it, but it was certainly impressive. Got me a few points on the evaluation.
Okay.
It's great. Handing out popcorn helps too.
Right. No, I was also, yeah, I mean, if you kind of see how it works in the 3D for the spheres. So basically the reason why
Yeah,
there's
I'm sorry, the 3D spheres when you're teaching this stuff is it's the next time I teach the course, I'm going to have our tech department 3D print me a sphere so that I can actually hold it in class and point to it. Because otherwise I'm doing things like this with my hands in class. You know, it looks like I'm doing a semaphore routine with the arrows going one way or the other. And you can't draw it on the board.
I was thinking maybe instead of doing like a 3D printed sphere, you might want to like like an LED sphere, and you kind of program the the positions of the LED, or the lit positions of the LED based on the what are the appropriate values. Um, just kind of was thinking like, that might be a way you can kind of show it. You hold a spear, but based on like one edge, and it basically the internal has like a connection to a to like a maybe a Arduino or kind of a normal circuit, just to kind of show how it does, or how the computations work uh, in it, or maybe connect it to um, like a computer or something, if you wanted to like program,
Yeah, I actually have one of those. It's winds up being about 64 LEDs in a three-dimensional shape, and you don't really need too much to drive it. But I think it would fall short in the resolution. I've seen people build three-dimensional uh, displays like that where they're like 8 by 8 or 16 by 16 on a side, but that gets your LED count pretty high. So
I'll tell you what I'm going to
can
do.
we,
I,
can we
yeah.
move on?
Well, what I'm going to do is move on, and moving on means moving to my last slide.
Okay.
Moving to my last slide, there's no content on my last slide. My last slide is just a reprise of my first slide. The book is called Quantum Computing Algorithms. I do lots of cool stuff in it. There are some good jokes. And if you want to get in touch with me via email, I am barry@burd.org. I welcome your communications. If you're communicating as a result of having watched this presentation, then please remind me that you've watched it so that I know to treat you with the highest respect. And I thank you so much for listening.
I have
Very
one
nice
question.
presentation, Barry.
Thank you.
Yeah, I
Yeah.
have,
Thank you so much.
Before we get into it, I just want to give a shameless plug for the book. And I'm so glad, Barry, that you showed that circle note, your unit circle notation. Going through that, it really does help you understand how the quantum Fourier transform and the inverse Fourier transform can pull those frequencies out of what appears to be thin air. The other thing I want to point out about the book, and Barry, correct me if I'm wrong, but I think you actually go through two complete separate examples or implementations of Shor's, or one of the algorithms. There was two.
I think there are three, but
two or three, yeah.
Yeah.
And I found that to be incredibly beneficial because most texts are going to take you through the basically what I'll call the textbook version, but you actually show, yeah, if you go out into Qiskit land, there's stuff out there that can make this happen faster for you. And so, yeah, there's three different flavors of it, and I think that's great. I don't think I've ever seen that in any other text that I've been through.
There's code for every example, code for every chapter.
Yep.
So, and it's all Qiskit. It's all stuff that you can run for free on the IBM cloud.
Well, that was awesome, Barry. Thanks. And so now, open discussion or questions.
yeah, I had Sunil. Can you hear me?
Yes.
Yeah, so basically it's kind of a two-part question. First part is, yes, I plan on getting the book. Second part is, where should I get the book from that will guarantee that you get a little bit of extra cash coming in?
I have not gotten, I shouldn't say this.
All right, where would you?
I
mean, I got three choices. I got
right, yeah.
PacT directly, Amazon, or find an affiliate link.
I just shop around. Whatever's best for you.
All right.
I don't write these books to make money. It's I love, yeah, go ahead. Yeah.
Yeah, it wasn't for you, to make money and all that, but so if I can shovel a little bit of cash away by buying the book, I'm not gonna grumble about that one bit. Yeah.
Yeah, no, just wherever is best for you.
Okay. So part of that is also I actually enjoy reading on a Kindle, but in this particular case, A, is it available on a Kindle, and B, is there a substantial difference between the Kindle version and the hard copy, assuming there is a Kindle version, in terms of rendering?
So I don't know if there's a Kindle version. I do know that they have PDF versions of it.
Okay.
Now, here's the problem. All right, let me put it this way. A PDF version is probably faithful and wonderful. And in fact, all the diagrams then, any of them that I made in color, you can see in color. There's only one diagram in the whole book that depends on being in color. And they've actually put it in color in the printed version. I was amazed to see that. Let's see if it pops out. But no, you can see it in all its glory in the PDF version. Kindle versions of books that I've written are often not very well formatted.
Amazon says there is a Kindle version.
Okay, I'd have to see it. I know that I've written books about Java where the Kindle versions came out and they turned the straight quotes in my code to curly quotes, so that if you try to copy it and paste it, you get an error. And I think there were even versions where all the indentation in the code went away in the Kindle version. So in terms of quality of Kindle version versus, I would go with PDF.
Okay.
Unless Kindle is doing much better with this book than with some others.
No, it's hit or miss with the Kindle.
Yeah.
So on the Java side, did you ever get the Java Cat? I picked that one up a long time ago because I started working with Java soon after it graduated from being Oak.
The Java Cat?
Cap. There's a Java.
Oh, the Java Cap.
Yeah.
Am I wearing a Java shirt today? No, if I stick a shovel anywhere in among my stuff here, I'm gonna hit some Java relic. It's got.
Yeah, no,
it's all.
I have a collection of those relics as well.
I
started
have them
using Java a long time
all
ago.
over the place.
Yeah.
The only reason I don't see one now close by is because I'm looking for it.
Yeah, no worries. It was just a completely off the wall question anyway.
Right.
I think, I think, wasn't there like a topic that you wanted to come back on?
So your question was parallel.
Yeah.
And here's the story. I mean, it's hard enough to get the hardware to do this business once, let alone to do it a useful number of times in parallel. So if I were to do that inversion about the mean, I mean, I would have to do it once and then again and then again and then again and then again in order to get it done, maybe however many times it needed to be. If I were trying to do it 16 times in 16 different circuits, I would need a number of qubits that might end up being larger than the number of qubits on any machine that I have. You got to realize that the number of qubits in a particular machine, in a machine that costs billions and billions and billions of dollars now, may be only something like 32 qubits. So we're not talking about having lots of quantum computers or quantum computers with many cores that we can do parallelism. But there is one phenomenon going on here that does reek of parallelism, which is that when I show you what 8 qubits are doing, those are 8 logical qubits. What's really going on inside the machine is there may be 800 physical qubits. And for each logical qubit, they're running 100 physical qubits and trying to find out what the modal answer is from those 100 qubits. So in other words, there's so much noise in quantum computers now that what we're calling 8 qubits may, because of the need for redundancy, be 800 qubits. In that sense, we have parallelism. We don't have parallelism in that we can have that we can have 100 circuits all running different copies of Grover's algorithm at the same time. Grover's algorithm,
Well,
yeah.
Yeah, and I'm wondering if what you're referring to by parallelism is we talk about running Grover's uh, algorithm. You're going to build the quantum circuit, you're going to load it on a machine, and you're going to run it, and then you're going to run it for 100 shots. I think what Vishay is talking about is instead of, you basically duplicate that circuit a few times, and instead of running it for 1,000 shots, run it for 500 or 250 shots.
Right.
What you're going to run into there is every machine has these noise profiles that are going to be affected by how many qubits in the system are active. And again, you're thinking about classical parallelism, where the classical things don't tend to interfere with each other. So in the current state of affairs, I learned recently that IBM's Eagle processor, which has 127 qubits, is now available on the free tier.
Wow.
I haven't verified that yet, but I know why they did it. Because there are some bigger machines that just hit the market. QEra's 256 qubit machine is now available through Briquette, Amazon Briquette. I was so excited to hear that until I found out what they're charging per shot of that thing, and it makes you understand that they've only got one machine online right now. So
What are they charging per shot?
It's 35 cents.
Wow.
Is what one guy told me. So you run a program over there, you want to run it 1,000 times, it's $350 for that run. So it adds up, and what it comes down to is they've got one dual mode neutral atom machine with 256 qubits available, I'm guessing, and you could access it through there, and that's why it's so expensive. They're going to need to bring the price down on that, because eventually they still are going to be competing with D-Wave because of the type of solutions they provide. But again, because these bigger machines are coming online, I'm sure that's why IBM made that decision to put their Eagle out there. And what you might find is, maybe they put one or two of them out there. Maybe you got to wait forever to use it. Who knows?
Oh yeah. Well, I created a random number generator used for raffles at the end of my Java user group meetings. Runs almost instantaneously on the simulators. The job queue, when I tried to submit it to a real quantum computer, said 5 hours to wait.
Yeah. And the times in their job queues are never at all accurate.
5 hours is definitely not encouraging.
No, and those estimates are they're never even close. But
Barry,
IBM
I have a question for you.
is also dropping their 5 qubit machines, so most of them are becoming at least a 7. But what can you? Basically, you're doing you're doing still pretty small, simple toy problems on that many qubits.
I have a question, Barry. So you said that the quantum machines cost billions of dollars. Is that a real number?
Wait a minute. I have to. Oh man.
You have to what?
I just realized that I had not stopped the share. And what that means is that our YouTube stream is just showing the last slide for the last, I don't know, half hour or so, and not showing us. So I just stopped the share. There we go. Okay, done. Yes.
So you said towards the end of the talk that, or maybe in the QA, that the quantum machines are costing billions of dollars. Is that a real number, or that's just something you threw out?
Ron, do you know how much these? I mean, I assume. I assume.
I don't know what it would be. If you add up all the research that's behind them, it's not hard to believe that it's at least somewhere in the 1 billion area.
Yeah, I mean,
I have no
you're
idea, really.
talking like for each billion-dollar startup, that's a valuation. So
Yeah.
the amount of money they're actually bringing in probably isn't even close to that. I don't know if they're millions of dollars, but like, I don't think it's close to billions. I did have a question about the algorithms because it seems like some of these I'm getting to scale as far as embeddings. Are you saying like for full PQCs that they just, if you add a qubit or add a gate, that they're difficult to scale like across the board?
Ask me that again. I'm not sure I understand the question.
So if you have embedding layer, your variational layer measurement, are you
Yeah.
saying across the board, like from you increase a qubit or you add a gate, that it's basically that it's not scaling?
No, I think what you might be hearing is that my explanations of these algorithms are intentionally small. So, for example, with the quantum Fourier transform, I lucked out because there was a set of roots of unity, points around the unit circle, where there were enough points so that you could see the cancellation phenomenon and not so many of them that you would get lost trying to figure out where along the circle the line was pointing. Now, if I had only a 4 vector to begin with, then it would be difficult to see the cancellation because there would be too little going on. If I had a 16 vector to begin with, then the way that you would have to visualize this thing would be pointing toward one, pointing toward a place sort of halfway up, then another one like that, then another one like that, then another one like that. So I think the sweet spot for that visualization is when I have 8 roots of unity. More than that is too much to visualize, too subtle to visualize. Less than that, you don't really see the cancellation phenomenon. I think that's what you were hearing.
Yeah, like in some of my, I'm able to use short embeddings instead of like a full, PQC to basically run 17 qubits when I need to, 20 when I need to, and I'm getting, static. I'm getting relatively good performance as opposed to like, if you're off by a quarter turn of the qubit, that type of stuff. So I think that's an area. It's basically feature embedding where you set 2 different data sets, different parts of the qubit, as opposed to like doing these, trying to get quantum speed ups and that type of stuff. Like it's just, it's just different. It's taking advantage of physics differently as opposed to like just pure speed.
Yeah, but you see, what you're talking about is physics. What I'm talking about is exposition, explaining these things.
Kevin,
I think we're in completely different. Yeah.
Kevin, can you tell us what PQC is?
Parameterized quantum circuit.
Yeah, so that
VQCs, PQCs.
it's not really an algorithm. It's a quantum machine pretending to be a layer in a machine learning stack, and you are using back propagation to tune the parameters to that circuit.
Right. Well, quantum machine learning for sure is the primary application for quantum computing.
Well, that's arguable, but okay.
No dollars,
Okay. Now, I mean,
well, I would disagree with that because I know people are making money on optimization problems on D-Wave and Penny Lane, and they're not using machine learning at all. They're just running graph-based or QBO problems through those machines, and they're working quite fine. So
Yeah, but it's still noisy hardware, like
yeah, but they're getting results. They're getting usable results, and that's
Yeah.
all that matters.
Well, I'm giving a presentation tomorrow that will cover this and just how practical the technology is, because it's safe and then it's just getting better performance. But like Sandbox AQ, NVIDIA, they do all the like 4,000 plus GPUs with QML, scaling everything up, national labs, the whole thing. But that's where the industry's going. There's going to be some room for big problems with small data, which is what quantum hardware is. But the bulk of it will be people just running QML all the time on classical hardware. That's just, it's cheap, it's available. You're taking advantage of quantum physics, but it's not like
the reason they call it QI is because it's quantum inspired. They're using things learned from quantum and back propagating them into classical circuits. You can add you can have this big farm of GPUs and you can run one hell of a quantum simulator, but every time you add a qubit to that simulator, you get to physically double all of your assets.
Well, there's no alternative. There's, quantum hardware has noise.
For those specific problems.
Right. There's no QML for hardware for probably over 5 years. And this is the application.
But there are applications out there.
Interruption. Oh, hello. Kevin, you mentioned that you're giving a talk tomorrow about this. Do you want to give pointers to that?
Yeah.
Leslie, yeah. Okay. What's happening? Oh, there we go. Okay, we put it in.
Yeah, so it's basically several months of FDA research that I've been doing with QML. And then this is putting it in terms of FDA as far as like probable benefit versus probable risk, substantially, equivalent predicate device, those types of things. And then just backing it up like table, industry, next one's medical industry, next one's all my stuff. And it's like, late nights. Hopefully I get my cast off tomorrow. For those that don't know, I was in a small car accident. But it's going to be a busy day tomorrow. It's going to be a late night tonight. I appreciate it.
I'm glad you're here healing up, Kevin.
Yeah, just at the stand-up desk and keeping the circulation going. But yeah, I mean, this is what I found is like you have to find something practical that everybody can use.
And not the practical man. I'm the in the sky man.
Yeah. Well, I mean, it's just how far can you wait? Like I took a look at all of this stuff and I was like, okay, well, Sandbox AQ keeps making moves with biotech and Kimmel and, Google Bard just made an announcement that they're using QML, which will be classical hardware. They had 2 announcements last week. So it's just, like I said, I'll be presenting on this stuff and it's just kind of pulling it all together here.
Yeah, I don't disagree that QML will be a major influence, but there are other algorithms out there. That's not the only game in town. You can D-Wave is making a pile of money on running optimization problems, and again, they don't go anywhere near machine learning. But D-Wave also supports QML.
So there's a question
not QIML. They actually support QML.
Yeah. So Bill, I'll answer your question here. When I started to code, I couldn't keep up with the newsletters. That's basically the answer to that one. And it was just too much stuff. And same thing with like, I just do one discussion a week because I'm running, notebooks. I try to run every day. But yeah, that's the core is getting a GitHub up and maintaining all that,
And Mark is saying, I thought security and quantum encryption was the most marketable practical application, at least currently. Thoughts?
Yeah, probably currently. Yeah, they're actually regular algorithms.
Quantum encryption is a bit of a misnomer. It's quantum key distribution is where people are making money. And quantum safe algorithms. So it's kind of a perpendicular issue.
Quantum encryption is a fun chapter to have written. Quantum key distribution. That was
quantum key. Quantum key distribution is where people are making money, and people coming up with quantum safe algorithms.
My chapter on quantum key distribution is named wait a minute, wait for it. A Fanciful Tale About Cryptography. It's a story about Bob and Alice trying to communicate with one another, and Eve being in the middle.
Classic.
Oh, I just was checking out right now. I was just at the PAX site, and it seems like just kind of maybe advertising a little bit for the PAX kind of publisher. They were saying like for the ebook it's $43.99, and for printed ebook it's $54.99.
I'm gonna be a millionaire.
Let's hope so.
Yeah.
Then you can buy us our own quantum computer.
That's right. That's right. That's right.
Okay.
I'm keeping my day job of teaching at Drew University.
But it does give you a little bit of like the hints of what's on the like each of the chapters and kind of the parts to the chapters. Yeah, so basically kind of shows you how the book is divided. I think the first part is or like third part is definitely more about the quantum computing, but you do have some stuff about explanation about what is a quantum computer and stuff.
I'm remembering a cartoon from long ago where someone's selling lemonade and it says $20 a glass, and the bubble atop the person's head is, well, I only have to sell one.
Classic. Yeah. So one other comment on the parallelism and the noise issues. Well, there are lots and lots of people, especially in IBM land, working on quantum error correction. I spent a whole week studying that, and there's a number of things that look promising, but it's like what you were saying earlier, Barry. It's like you don't have qubits, you have logical qubits, and instead of you're not using one qubit, you know you might not be using 800 behind it, but in quantum error correction, you might have 16 to 1, something like that. And they're showing reasonable results in lowering the noise problems with a number of different algorithms. And oddly enough, some of those error correction algorithms have parallels in the classical world, and they use a lot of the same theory. It just it has to be mapped into quantum circuits, which again are not circuits. You have to think about them slightly differently.
Yeah, I remember your
yeah. So I'll leave this.
Ron caught me on the wording.
Yeah. So one last comment about that difference is a quantum circuit is more like sheet music. Those things that you see on there, the wires are timelines. They're not connections. And the things you see on going from left to right are events in time. This differs from a classical digital circuit in that digital circuits have those wires. Digital circuits do their job continuously. Quantum circuits don't. You run the thing by sequencing the state of the machine through each step. So that's why you can't solve your quantum problems if you get locked into thinking, well, this is how I would do it in digital. It'll slow you down.
I think the other problem with thinking digitally is that in digital thinking, we're used to putting together a puzzle with steps that are very familiar, loops and branches and assignments. But
again, once you build a digital circuit, it does it for the rest of its life.
Yeah.
It's continuous, and this is not how quantum works. Quantum is more like, again, playing a musical instrument and adding the notes together.
Yeah, so going back to the error correction, a lot of the Qiskit, so for me it's 9 a.m. I think Eastern it's noon on Fridays. I think we have anyway, still use regular machine learning and even quantum machine learning to try to, predict noise or fix noise in circuits. And it's a very common
Absolutely. Yeah.
subject that they have on, trying to see if it's most Fridays that they have it. And
Yeah, it's 12 noon Eastern time. It's the Qiskit Live channel for anybody who doesn't know about that. Highly
I've been
recommend.
trying to do, I don't know if anybody does the Mondays. It's like Monday, I think same time, like 12 Eastern, 9 Pacific AM. And it's like a developers thing, but it's only like twice a month. And I've been trying to catch that one too.
Yeah. Yeah,
But it's like the official
those are
thing.
very good. Just be prepared to be in the swamp a lot of the times, because they have talks by people who are talking about a very esoteric, highly technical thing, and they've spent years working on it. So, but it's good to watch them, because some things will fall out of it that'll make sense to you, and but you get a really good idea of where those problems are and what a bunch of people are trying to do to fix them.
Yeah, there's a lot of stuff that's just over the head if you're not in that specific thing, but it still helps because like you're
Yeah.
listening to experts talk about quantum computing and you will pick up on some things.
Hey, Barry,
Absolutely.
before we stop, I just wanted to ask you a question real quick. I go way back in computer textbooks, back to the 5 1/4 disc days, 3.5
Not the
inch disc.
eight and a half. What was it? 8.5?
8 inch.
I never saw one of those in a book, but I saw plenty of 5 1/4 and 3.5, and then plenty of CDs and DVDs. So I was just going to ask, have you created a companion website for your book that you can share in the chat so that we could kind of go look at what you were sharing on that website?
If you visit allmycode.com,
Okay.
what you will find is the world's plainest, perhaps ugliest website that I created by typing HTML, and it has pages for all the editions of my books. At
You
least,
could probably sell that website.
well, there isn't a lot there yet for this book, but allmycode.com. If you want to see a website that looks like, remember Gopher?
Oh yeah.
Mosaic. If you want to see a website that looks like that era, go take a look at allmycode.com. And it's got pointers to scholarly papers that I wrote and interviews that I did and all kinds of other things.
I'll be going there tonight. Thank you so much.
There you go.
Those kind of websites are the best.
Yeah, it looks like you've created a lot of material here.
Wow, I've lived a long time.
Don't you also have a GitHub repository for the?
Nothing. Oh, there's a GitHub repository for the book, but
for this book, yeah.
But the publisher maintains that.
Oh, okay.
My own personal GitHub repository is, and social media. I was putting my Twitter handle in my Java books, but there's too much noise on Twitter. I can't figure out what's, so the email, I put my email address in the books now.
Yeah, they have like your solutions. There's a Python notebook and a markdown for every chapter on one of these. And like the practice, maybe.
There at the end of each chapter, there are about 8 questions for practice.
Well, it's doing pretty good. You already have 6 stars, and that was what, September 7th.
That's cool.
Yeah. You can actually host a website on GitHub, put an index file, and there's basically what can't you do with either Git locally or GitHub online.
I'm too busy grading papers sometimes.
Okay. Any other questions? I can't believe we're coming up on 2 hours. It's really gone by quickly.
I thank everyone again for coming and listening to me, and I enjoyed the dialogue, and wonderful. Thank you.
Well, thank you, Barry. This has been really quite rewarding, and it's been a journey. We've been watching this happen for some time now, so it's just so cool that it's a publication that's out there on the streets, and everybody should go grab one.
It's for real. And stay tuned for more of our quantum computing Chicago and Illinois and beyond meetup sessions. Is that what we're calling ourselves now?
That's what we are calling ourselves.
Keep your eye on our meetup page. Do whatever one does to be able to look at it often, and hope to see you again soon.
Yeah, and good luck with the books. Like, you could definitely rotate them too, because you got Java, beginning programming with Java, the quantum stuff.
I'm a regular Stephen King.
Oh yeah.
Yeah, so the meetup name is now Quantum Computing Chicago, Illinois, and beyond, because we are going to threaten to become a global quantum entity. And
you have allmycode.com. So that's good.
Today gone, tomorrow the world.
Yep.
sounds like a plan. So all right,
Okay,
everybody.
thanks everybody.
Thanks for the
Everybody
questions,
later.
Kevin. We'll probably see you tomorrow.
All right, sounds good.
Bye-bye, everyone.